Welcome to this lecture series in number theory. We have previously seen that there are infinitely many primes. Today we will prove a slightly more refined result. So given any odd number, either it will be of the form 4k plus 1 or it will be of the form 4k plus 3. There are only two possibilities for an odd number. Either it will leave the remainder of 1 modulo 4 or the remainder of 3 modulo 4. It cannot leave a remainder of 0 modulo 4 or 2 modulo 4 because otherwise it wouldn't be an odd number, right? And any prime greater than 2 is necessarily odd. So there are therefore two kinds of odd primes. One which are of the form 4k plus 1 and the other of the form 4k plus 3. Now we know that together they are infinitely many, but one can ask, how about just the primes of this form? Are they also infinitely many? And how about the primes of this form? Are they also infinitely many? Right? So we will answer these questions, and here is the main ingredient that we will need. We proved this last time. If P is a prime and suppose A is invertible modulo P, meaning A is relatively prime to P, then order of A modulo P exists, and the existence was proved long ago. What we proved last time is that it divides P minus 1, and this will be crucial. Okay, so let's proceed. Some problems for practice. And now let us get started. So first we will show that there are infinitely many primes of this form 4k plus 3. Right, and as discussed in the intro, there are only two kinds, either 4k plus 3 or 4k plus 1. We are talking about odd primes. There are only two kinds of primes then. So first we will establish that there are infinitely many of this form, and then we'll talk about the other. So it's a very interesting question. You should pause the video and think about it. Take it as a challenge. All right. So here is the proof. Here is a proof. There should be infinitely many proofs of this. So recall what we did to prove that there are infinitely many primes. So we fix a integer n, let n be some natural number, enough to show that there is a prime P such that P is greater than n and P leaves a remainder of 3 modulo 4. Right, this is essentially restating the proposition. Okay, so now recall, how did we prove that there were infinitely many primes? We considered this number, and then any prime divisor of it must be greater than n. That was easy. So we may try a similar approach. We have to modify the number that we consider to somehow account for this kind of prime factor. So I think if you worry about a little bit, it is natural to think of the following. Just multiply n factorial by 4. This seems to be going in the right direction. But even here it is unclear what to do. Like, there is no way we can say, or there is no obvious way we can say that this number must have a prime divisor of this form. But then again, it would be quite natural to modify this also a little bit and consider this number instead. Now, this number must have a prime divisor of this form. Why is that? Suppose this was written as the product of primes. So suppose we write this as P1 times P2 times P R, let's say. So we have written it as the product of primes. We are not insisting that these primes are pairwise distinct. They are just primes that appear in its prime factorization. So you may write powers if you like, but I have not written powers because I am allowing for repetitions. Now if each of them were of the form 4k plus 1, if none of them were of this form, note that first of all none of them can be equal to 2 because this is an odd number. So none of them can be equal to 2. So each of these primes are odd, correct? And now if each of these primes were of the form 4k plus 1, were of this form, then the product will also be of this form. If you have two numbers which both leave the remainder of 1 modulo 4, their product also leaves the remainder of 1 modulo 4. Right? So that would contradict this equation, because the left side leaves the remainder of 3 modulo 4 while the right side will leave a remainder of 1 modulo 4. So amongst all these primes that are written here, at least one leaves a remainder of 3 mod 4, but we are not still out of the woods yet, because it's not guaranteed yet that that prime will be greater than n, because that prime could be equal to 3. Note that 3 divides the left hand side. 3 divides n factorial, and 3 clearly divides this. So it's still not over, but with one more modification it's over. And there could be another simple modification to get to the same place, but this is probably the simplest. So now write this as the product of primes. We claim that one of these primes is of the form 4k plus 3. This is same as the previous reasoning, no difference. Right? If all of them were of the form 4k plus 1, then so would this be, but this is not of the form 4k plus 1. Okay, so there is at least one prime which is of the form 4k plus 3. Let's say pi. So say we claim that pi is greater than n. So why is this? Well, if pi were less than or equal to n, so the proof of this is, suppose not, then pi is less than equal to n, and hence pi divides, well, the left hand side. This it divides simply because it divides the right hand side, but it also divides 4n factorial. So it divides their difference, and we see that pi divides minus 1. But that's a contradiction, because pi is a prime. This would mean that pi were equal to 1. So pi is greater than n. So we have found a prime congruent to 3 mod 4 which is greater than n, and that is what we wanted to do. This is what we wanted to show. So slight modification of the original argument leads us to this. Okay, I hope this was clear and instructive. And now let us proceed. Now for the more interesting one, we want to show that there are infinitely many primes of the form 4k plus 1. Alright, I encourage you to pause the video and worry about it. Here is a proof. We may try a similar approach. Just like in the previous example or previous proposition, we might consider this number. We might consider this number. Again, what we want to do is we want to show that there is a prime greater than n. We have fixed some natural number n. We want to show that there is a prime greater than n, which is of this form, which leaves a remainder of 1 mod 4. So fix n greater than 1. And blah, blah, blah. I'm not writing the enough to show that part. Okay, so let's see why. Here, it is not very clear. In fact, it is not clear at all as to why there should be a prime factor of it of the form 4k plus 1. If there were, then we were done. If somehow there was a prime factor of this guy of the form 4k plus 1, then we were done. But how do we ascertain that? We cannot. The problem is this. If you multiply two numbers of the form 4k plus 3, if you multiply two numbers of the form 4k plus 3, you get a number of the form 4 times something plus 1. Because 3 times 3 is 9, which is congruent to 1 mod 4. So it is possible that all the prime factors of this guy are of the form 4k plus 3, and that therefore doesn't help. Okay. So what do we do now? So here is the very clever idea. You consider this number. Call this m. Okay. Right, and now let P be a prime divisor of M. And it is clear, note that P is greater than N. So that part is fine. Because if it were less than or equal to N, it would divide this guy. It already divides this guy, so it would divide 1, and that would be a contradiction. So we are interested in showing, in fact we claim, that P is of the correct form. Alright, so let's see why. So we have this number, this plus 1 is congruent to 0 modulo P, because P is a divisor of it, which implies this is congruent to minus 1 modulo P, which we will write as 2 times n factorial squared is congruent to minus 1 modulo P. And instead of 2 times n factorial, let me write x. Just a change of notation. X is nothing but 2 times n factorial. So what I want to do is, in particular, this implies that x to the power 4 is congruent to 1 modulo P. Right? So we have this number x, and these are the powers of it. And we see that this is congruent to 1 modulo P. So the order of x modulo P is at most 4. So we see, from this we see that the order of x modulo P is at most 4. Alright. Now, so, these are the powers of x. So this cannot be congruent to 1 modulo P, because if that were the case, x square would be congruent to 1 modulo P, but that's not true. X square is congruent to minus 1. So certainly x is not congruent to 1 modulo P. X square is congruent to minus 1. Already we see that it cannot be congruent to 1 modulo P, so that's also fine. So order is at least 2. In fact, at least 3 now, because it cannot be 2. The order of x cannot be 2. It is at least 3. But can this be the order of, can 3 be the order of x? So if 3 is the order of x, then x cube is congruent to 1 mod P. We already have that x square is congruent to minus 1, so let me write x cube as this. Right, but that gives that x times minus 1 is congruent to 1 modulo P, which gives that x is congruent to minus 1 modulo P. But now squaring both sides, we get x square is congruent to 1 modulo P. But we already knew that x square is congruent to minus 1 modulo P. So we get that minus 1 is congruent to 1 modulo P, which implies 2 is congruent to 0 modulo P, which means P divides 2, and which means P is equal to 2. P is a prime. But can P be equal to 2? Well, P is a divisor of this number. This is an odd number. This is not divisible by 2. So no, so this is a contradiction. So order of x cannot be 3. So this is also not congruent to 1 modulo P. So what we deduce that the order of x modulo P is actually equal to 4. It was at most 4, but by this reasoning now it is at least 4, and hence it is equal to 4. So the upshot is, we have deduced that the order of x modulo P is 4, but by what we recalled as a consequence of Fermat's little theorem, this implies that 4 divides P minus 1. And therefore, this is another way of saying that P is congruent to 1 mod 4. And that proves our claim. this is exactly what we claimed. So very interesting piece of reasoning and not obvious. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.